Hello, everyone, and welcome back to Handmade Hero. It's been a while, and rather than jumping right back into programming, I felt like that would probably be ill-advised since it's been a long time since we've done a stream. We actually moved, and so the streaming location is completely different now. I think everything's fine. We did one test stream, and the internet held up reasonably, and the recording setup held up reasonably, so we're hoping that will be the case, but we don't actually know. So what we're going to do today is a little bit lighter than full programming. We're just going to take a look at some stuff that came up on Twitter recently regarding how the front end of a CPU handles clears. And I just wanted to kind of go through the basics of this sort of thing because it's a good... less so than just understanding how an XOR clear works on a CPU, because it is worth knowing that as a specific thing, but also just understanding how to sort of like read the assembly at like a basic level that comes out of the compiler and understand whether or not it's producing something reasonable if you're trying to do like testing of what it's doing. That can be kind of difficult. And so I kind of wanted to walk through one of these just so you could see what's going on and get some experience with that process. So if you, I guess the easiest way to do it would be to like walk through what actually happened. So there was some talk about clearing values to 0. This was a separate thing. Regarding like language design stuff that I actually don't care about, but the part about clearing to 0, I do advocate. I think 0 clearing is probably one of the most underappreciated things in computer programming, and in fact, I highly advocate like what I would call ZII is a term that came up with a long time ago. 0 is initialization. It's to kind of combat the RAII phrase. Which I don't think is valuable. So resource acquisition is initialization, I think, is a bad programming practice. I don't think it's good. I don't think it leads to good program structure. But ZII, which is 0 is initialization, I think does lead to good program structure. And it's actually not just about clearing to 0. Clearing to 0 is sort of a separate thing because you can imagine programs that are just written exactly the same way as they normally would be, but you insert a 0 clear before every use of a variable, right? So you just assume that if a variable is uninitialized, it actually gets cleared to 0 or something like that. There have been languages that do that. There are also like extensions to C++ that do that, I want to say. I feel like Microsoft actually introduced something like this in some research structured programming projects that they did. They have divisions at Microsoft that do things involving compiler and error research and such. And they periodically do things like introduce static code analyzer things, and they actually try to deploy them like at Microsoft to try and find bugs and things that are like huge and unwieldy, like, you know, Microsoft Word or something. Like you're talking about like legacy code base, hundreds of thousands of developers, millions of lines of code probably, right? And they try to deploy things, and I think they had some things they deployed that in addition to static last, like clear to 0 stuff. I don't know. So this is not like new. Like clearing to 0 is old and not like anything that you haven't seen before if you've been around a while. ZII, on the other hand, is like actually pretty different. I haven't seen it discussed much. I don't know if it has a history or not. It's just something I kind of came to on my own, but I know that other people also kind of came to it on their own, at least something like it. And the idea behind ZII is just that you try to structure your program so that 0 is valid, right? And that's different than just clearing to 0. So an example of how that would work is if you have only 2 valid states of your program, let's say one where the value of a variable is supposed to be 3 and another where the value of the variable is supposed to be 4, you would actually change that program so that the correct values are 0 and 1 instead of 3 and 4. And then you'd offset the 3 by 2, right? So you'd add 2 to the variable, so you get 3 or 4 depending on 0 or 1. That way, no actual initialization is necessary for the default case. So basically, ZII means transforming a program as much as possible into the state where all zeros is actually the like starting run condition, rather than thinking of some random set of values that you want as the starting condition and trying to enforce that those actually get set, right? And so, again, big proponent of this model. It has a lot of advantages. Number one, it makes it much harder to introduce bugs. But number two is that it's actually way more efficient, because rather than having to keep all of this data on hand that you use for initialization, that you're constantly like pulling into the cache to copy into things, and having to like actually have structured pieces of code that go through and switch around to know how to initialize things, you can literally just initialize like giant sections of your program simply by allocating and zeroing a block of memory, which is way more efficient, especially because the first time you do it, you actually don't pay for it, because the operating system usually has to hand you a zeroed page to begin with, since security concerns on modern OSs means that they will zero the pages whether you want them to or not. For example, on a PC, there is really no way to allocate anything other than a zero page. The operating system will never give you back anything other than a zero page, so you can't actually get a performance win by not clearing memory. The memory will be cleared, and it will be cleared by the OS. And again, the reason for that is because there are really significant security concerns to the operating system recycling memory, because that memory wouldn't necessarily have come from your process, or even if it did come from your process, it doesn't really necessarily know whether it came from your process in a way that's safe to allow you to reuse it. So when you call virtual alloc, you always get memory that's zeroed. That's just a specification of the OS. And to the best of my knowledge, there's no way to turn it off. You would have to be doing some kind of kernel bypass thing or something. The average program that just runs on an end user's machine, again, to the best of my knowledge, has no way, without like special administrator privileges or something, of actually getting a non-zeroed page. So what I wanted to talk about now was something sort of tangentially related to this. That is just a programming model that I think is good. You've seen me do it on Handmade Hero before. I actually do it even more now, like in the past 5 years or so over course of Handmade Hero. Definitely some things have happened to my programming that I think make it better. I mean, you never really know whether you're getting better or getting worse, right? But and I actually apply ZII a lot more now than I did. So like, if anything, I feel like it's on the rise in terms of the number of places where I find it useful. The other big one would be multi-threaded. Like, I feel like I'm 10 times better at multi-threaded now than I was starting Handmade Heroes. So the multi-threading stuff in Handmade Heroes is kind of crap, but you know, you're always learning. There's nothing you can really do about that. You're always going to look back at programs that you wrote and go, wow, this is garbage. If you don't, it's usually a bad sign, because it means you've kind of stagnated, right? So I never really beat myself up over that sort of thing. I just go, look, if I can't look back at a previous project and find something I did stupid, then it must mean I stopped learning, because no one's a perfect programmer. And so if you look back and you say, wow, this is all great, it's probably not a good sign, right? It probably means you haven't been pushing yourself very hard, and that's usually not good. So anyway, what I want to talk about today is tangential to this. Again, I talked about this a little bit on the pre-stream, but I'll talk about it again. On Twitter, a fellow named Jesse Meyer from NASA was responding to some of the stuff regarding ZII with some stuff that doesn't really have anything to do with ZII structurally. It's just about looking at the performance. Something I said about clearing to zero being free in a lot of cases. And I don't actually know why he was interested in this, but he maybe just wanted to look into it a little bit. And so he posted some test code he was trying to run, and you can see it here. It's basically a piece of code that creates a little fictitious matrix type here. So a 4x4 matrix, homogeneous 3D matrix, like the kind you would normally see in graphics programming. And he then allocates a large number of these. So you can see here that he's got a 10 million matrix alloc. He just allocates a flat block of memory. He does a clock, and he then runs through the memory, and he does some setting of it, and he did it in two versions. One has this zeroing commented out, and one has it commented in. You can actually see here with the 0 removed. So he was trying both of these. Now, there's some things I want to say ahead of time about this, because so if you look, you can see on the command line here that Jesse was using DOS, which means there's certain things that are not necessarily at play that would have been at play if he was using Linux. And I want to mention that real quickly because a lot of people don't know this. I've actually been bitten by this multiple times, so I want to just point it out because if you're coming from DOS, it can be a little disquieting. So the first thing I want to say is when you're doing a benchmark and it looks like this, and you do a malloc of a large block of memory, and then you do a timing run, one of the problems that you will get is that if you actually structure your timing loop like this, where you do a begin and end, and then you do the whole thing inside the begin and the end, you can run into really significant performance penalties that are not accurate, that don't reflect the actual performance of the routine inside, because of the fact that the operating system is under no obligation to actually have mapped this memory yet. So on Windows, usually what happens if you call malloc, it's going to thunk through to virtual alloc for something this large, and it's going to give you back a very large piece of actually committed memory, usually. And then when you run through it, you're not really page faulting necessarily, right? You're writing through that memory, and it probably already got set up in the memory mapping tables. So that's all fine. And this was on Windows, so it was probably fine. But again, to avoid any kind of secret surprises while we're talking about this kind of profiling and this kind of looking at detailed information about how the processor works, it's important to remember that on Linux, that is not true. So on Linux, if you allocate a very large block of memory, while I'm not exactly 100% sure all the things that malloc might do, because malloc is actually a runtime library component, but the equivalent to virtual alloc on Linux is memmap, so it's mmap. You can look it up in like the man pages. mmap is exactly like virtual alloc in terms of what it does. It sets up memory mapping tables for your process so that you can create pages of memory that you're going to use, but it operates in a very different way than virtual alloc. When you call it by default, what it will do, even with the kinds of settings that you would normally pass to virtual alloc, is rather than ever actually allocating any memory for you, when you ask it for something like this, like 10 million matrices, it will actually only allocate 4,096 bytes. It actually won't even really allocate 4,096 bytes. What I should say is will map a phantom page, a 0 page, of 4,096 bytes. It will point the complete range that you asked for at that 0 page, and it will set it to copy on write. So what it will do is when you actually touch a particular page of memory, it will go and map a real page at that time that you first touch it. And when I say touch it, I mean write to it. So if all you ever did was read from it, you would literally never map any memory. So for example, on Windows, if you virtual alloc 16 gigabytes of memory with a commit, like, so if you actually, use mem commit, not mem reserve, you're actually saying, hey, I want to actually map this. It will actually allocate 16 gigabytes of memory. And if the machine doesn't have 16 gigabytes of virtual memory to spare because the page file isn't big enough or something, that will just fail, right? On Linux, as far as I know, and again, I don't program Linux that often, so you'll have to forgive me. There may be certain configurations that interfere with this or certain behaviors that will change, but generally speaking, if you try to memmap 16 gigabytes of memory on Linux, as far as I know, it just works because it never actually allocates any memory. So the only time that I would think that there could be any real way that that could fail, meaning it would actually return like a 0, is if you tried to allocate so much memory that it was outside like the bounds of mappable memory completely, like if it blew past the 48-bit barrier or something like this, where you were into a range where it was impossible to even map the memory. But at no time, as far as I know, does Linux actually look to see whether it actually has enough virtual memory left available to give you that memory. It's only going to do that later when you actually write to it. And whether or not this is a good idea, I suppose, is debatable. I think it's horrible because I care a lot more about reliability than I care about like weird performance tricks like that, where you're like getting a little bit extra in the case where an app doesn't really need the memory or something. So I really don't like that, but, you know, Linus and Dave can fight that out because I'm not really experienced enough with OSs to come down definitively on one side or the other as a system programmer or anything like that. But as an app programmer, I really don't like it. Suffice to say, it happens. So you need to be aware that that is occurring. And even though in this particular case, we don't care about the failure state. For example, the case where we're asking for more memory than the machine can actually provide in the mapping. And if we were to actually touch them all, we don't care about that because this is a test program. We're not shipping it to an end user or anything like that. So if it fails, it fails. We can work around it. But what we do care about is the very odd access pattern and performance pattern that will occur the first time you attempt to write to the memory that you've allocated. And so, like I said, in Jesse's case, he's using Windows, so probably this wasn't a problem for him, and his timings probably weren't affected by this. But if he had chosen to run this on Linux, he would have been. And the reason for that is because rather than the time taken to pull these pages in and give them actual virtual memory addresses for real, where they're really mapped to real pages, not to the 0 page, normally in Windows, this will probably happen on this line, which is before we take the start clock. But on Linux, it will happen inside this loop. And it will specifically happen every time we cross one of those 4K page boundaries, unless Linux is set to a larger page size. I assume Linux can be set to 64K pages or 2 meg pages or something, but I don't actually know. Again, I'm not really a Linux programmer, so I don't know. But point being, usually 4K pages is a safe assumption on a lot of machines, but it could be more. Every time you cross that page boundary, you will actually page fault, and this clocking here will actually measure the page faults. So runs 1 through 25, or run 1 through 24, I should say, will be reasonable runs. Run 0 will actually be totally wrong. And since this clocking here is actually taking that into account, it's worth noting that when you're trying to do things like examine performance, you really don't want to have that happen because page faults are so expensive that they may easily dominate the measurement time that you're actually seeing, and the actual cost of the thing you were trying to measure may be a very small fraction of that, leading you to believe that there's less effect on the time of the program than there really is. So usually when you're doing this kind of timing, what I would recommend, depending on what you're actually doing, there's 2 approaches you can take. The Wild West, ride into town with guns blazing, cowboy time, fun, fast way of doing it is you actually put the clocking, and usually you use more accurate clocking than clock. Usually you would use query performance counter on Windows. But you put that inside. So inside the for loop, you put the begin and end in here. And what you do is you take the smallest time. So you initialize outside the loop to, like, the lowest time is infinity, right? The highest value for the thing you're tracking. Then inside the loop here, each time you do a begin, then you do the for I over the entire end, then an end. You take the difference between the 2 of them, and you, if it's less than the previous minimum, you use that one. Furthermore, what some people do is they even they keep it looking like this basically, and they put the for I loop around the outside, but rather than being a for I loop, they use a while loop. And what they do is they do a for I of 25 runs or something like this. And if it goes down from if inside here, so I'm not explaining this well. You put the clocks on the inside of this thing. So you run it 25 times, and you do the thing at the end. Inside here, you do clock begin, clock end. You check the time. If it's lower, you keep it. But then you've got a while loop on the outside that says, if during any of those 25 runs, I found a new minimum, run it again. So basically, that just keeps running. As long as it can get a lower time value, it just keeps running. And that's basically like a hunt for the minimum kind of routine. A lot of times you want to use, that's why I call it the Wild West way, because it's not a good measurement of what the routine will actually cost in practice, because it's kind of the best case scenario. It's finding the best case scenario of whatever this thing is. But it's a good way to find out what's going on in the processor, right? Because if you're trying to figure out what the minimum possible execution time is for something, when all the stars align and the caster's in the best possible state and the branch predictors are in the best possible state and everyone is just happy and wonderful, what is that time? Hunting for the minimum is the way that you get that, right? So in this particular case, again, this particular way of running it is particularly susceptible to the page mapping problem. And like I said, the reason for that is just because since it's timing the entire set of runs rather than, say, hunting for a minimum, if you ran this on Linux, you would get totally screwed. On Windows, you probably won't get that screwed, right? Okay, so as I said, there's a second way that people often try to time these things, and that is that you do basically the same thing I just said, which is you put the clocks on the inside and then do a bunch of runs on the outside. But and again, usually use a higher perf clock than clock if you're actually trying to time stuff precisely. But point being, whatever your timing function is. And then what you do is you take a statistical look. So you like histogram and make buckets for how, like, where did I see the times landing, right? And you maybe ignore some outliers, like if the operating system decided to swap you out at that time, so you would count like a huge kernel transition in there, for example. That's an example of a place where you really don't want to count that time against your average, let's say. Or if you find you get an extremely fast run and you've never seen it, and you never see a run that fast again, maybe again that was a case where all the stars aligned and that's really not a realistic expectation of what will happen. So a lot of times what people will do is they'll look at a statistical breakdown, right, of what actually was happening in the routine. And so that's one way you can that's one way that you can go in and get another picture that's not just hunt for the fastest possible. It's like try to get a picture for how this scatters around. Now, in either case, again, it's never, when you're creating a test case like this one, we're usually investigating something specific about the processor. So I would probably recommend the hunt for the minimum if we were going, because again, what Jesse was trying to do here was investigate something the processor was doing. He's not really trying to figure out like what this routine does in the real world, right? So taking a statistical breakdown of it doesn't make a lot of sense because it's already a synthetic test case and we're not really trying to figure out anything about how it actually would behave in the real world. What we're trying to do is investigate something about the processor. So hunt for the minimum makes a lot more sense in this case, and that's probably what you would do if you were going to upgrade this to a little bit of a stronger analysis, right, for looking at what the processor does. Probably not statistical breakdown. Unless you were trying to capture something else. If you were trying to capture statistical breakdown, you probably need a more complex test case because this is so compact and so straightforward that it's unlikely that you're going to capture a lot of weird things about cache behavior or branch prediction. or hyperthreading or whatever. Like, we're just not going to get that here. So statistical breakdown doesn't make a whole lot of sense to me, but, everyone has their preference. Okay. So with all of that preamble out of the way, which again, all of these digressions are intentional because I'm just trying to give you a full, the only reason I'm doing this today is just to give people a firm understanding to the extent that they can get one about how this kind of process works and what to be aware of. So again, like, maybe this is sufficient what's already written here. Maybe it's not, especially if you're running on Linux, it would be bad. On Windows, maybe it's fine. If it's not fine, you may want to move these on the inside. You probably want to switch to higher resolution timers. A lot of these things are important for investigating CPU performance because CPU performance is subtle, right? So you need to be careful about how you do it because even if you're just trying to get a vague understanding of what's happening, there's so many things at play that sometimes you have to get a little bit more precise, so it's hard to say. But this is sufficient for our purposes for now. What I wanted to go through, I tried to recreate this routine in Godbolt so you can see it here. I've not compiled it, so I don't know if I have a typo or something. So what I'd like to do is I'd like to just compile this really quick on the actual machine to make sure that I didn't screw it up, right? Because I just kind of typed it in and I wasn't particularly careful or anything. So I want to make sure that I don't have any kind of like stupid error in there that's going to make it so that I don't, let's just call this XOR clear or something. I don't want to have anything in there that's really stupid that's going to make it so that we're looking at assembly code that's actually totally wrong and doesn't matter, right? Because if I screwed up the code and it doesn't actually work, then the assembly that we're looking at isn't a reflection of anything at all. It's just fictitious and wouldn't matter. So I just want to run it and make sure, get rid of any crash bugs, get rid of any, if it prints out completely wrong values or something, right? So I just want to go ahead and compile this here and run it and see what happens. Just so, again, I can get a feel for what's actually going on and make sure there's no obvious bugs. Value check is 1, which is what it should be, so that's good. And if I actually go in here and do an O2 on this, it should get faster, and it does. So I think we're good. Like, I think I probably didn't screw it up too bad, and that's really what would matter in this case. So let's pop back over here because what I wanted to go over was nothing in particular about actually running this code. I wanted to go over the assembly language. And so what I'm going to do is I've opened up Godbolt here and I've got that code basically exactly as Jesse wrote it. It's more or less the same. I maybe changed some names and wrote it in the style you're used to seeing on Handmade Hero, but other than that, it's basically the exact same code. I also included XMM and trin here because I'm going to want to play with intrinsics a little bit later on, so I just put in the ability for us to access the intrinsics as well, but otherwise it's basically the same code. And what I'm going to do is just make sure that I have both compilers here. I don't really remember how to do this exactly. Yeah, there we go. I have a little trouble with the interface of Godbolt sometimes, but once I get it set up, it's nice. So I'm just gonna pick an MSVC with an O2 here, and so that we can look at both pieces of code. And this way we have, you can kind of see here. This way we've got an example of what Clang will output when we tell it to optimize. And we have an example of what MSVC will output when we tell it to optimize as well. And just looking at this, I mean, this tends to be what I see, and it's weird. I don't know, like maybe I just always happen to drop in and inspect assembly at times this happens, but just whenever I look at assembly of scalar code or like code that the compiler was supposed to make for a simple routine, MSVC always seems to totally beat Clang from what it looks like. Like it just always MSVC's optimizing compiler just always outputs like better stuff for my code. And then the opposite is true anytime they're intrinsic. So anytime I write like heavy intrinsic code, not anytime, I guess that's not true, but a lot of times when I write heavy intrinsic code, it seems like Clang actually does better. I don't know. These may be a little bit, again, just like selection randomness bias, like I happen to see it certain times and not. But it's just weird. And when I look at this, you can kind of see, even just from the start, what you can see here is that when it's actually generating this code, like it looks like MSVC just totally crushed it. Like it looks like it's just using a rep to move these guys, and I mean, I feel like that's exactly what you would want most of the time. Maybe I'm wrong about that, but I feel like that would absolutely destroy this nonsense, which doesn't even look like this doesn't even look right. Just even if you were going to do like I'm going to walk through both of the assemblies, but this just looks nuts. I have no idea why you would ever do this. And again, I'm not really an optimization guy, so like my opinion of whether this looks nuts or not is maybe not the most informative, but I mean, just like at first blush, I can't see why you would ever want anything like this code for this loop. It's just plain nuts. Whereas this looks exactly like something I might want for this loop. So I don't know, like I don't know what to make of that other than to say that it kind of reinforces my opinion that Clang has a lot of weird, bad cases hanging around in it that just don't seem to happen for MSVC. And sometimes, like I said, in certain circumstances, it seems like Clang has a much more aggressive optimizer that will do some really cool stuff in certain circumstances. But on the average, it seems to have really dumb problems that it always screws up, right? And this is an example of that. So let's walk through what this code is actually doing before I start talking about XOR clears or any of those sorts of things. As you can see, we don't do any clearing here. All we're doing is basically a glorified memset. So inside the loop, and what you can see here is, if you're not very familiar with assembly language, then the way to think about it is just innermost loop of your code is usually pretty easy to identify. In Godbolt, it's especially easy because you can actually move over it and it will show you, and it also has them kind of color-coded, right? So you can see when I move my cursor over here, it like highlights this, and when I move my cursor over here, it highlights that. So you can actually see the body of the loop in question, and you can even see where the criteria for the loop are. So you see as I move over that, you can see that it's highlighting this piece of code here, right? And so one of the nice things about Godbolt, and the reason I often tell people when they're learning assembly language to please take a look at it, it's a very nice tool for this, and it's the kind of thing that you would want built into your editor, and so it's too bad it's not built into most editors, but it's not. And so when you're actually looking at the code here, it just helps because if you don't know how to read assembly language and you just had, like especially on this side where there's not labels in this one, because of the way that it turns into a rep. But you look at it as just a giant wall of assembly, and if you're not very familiar with how to read assembly, that can be very daunting, and it can be hard for you to figure out where you're looking at and get any kind of foothold on it. But when you have Godbolt, you can just move over it and see where it's coming from, which makes it a lot easier for you. So when we actually look at this code, we can see what it's doing, and let's go ahead and walk through what's actually happening. So as you can see, this particular for loop here has evaluated to effectively this piece of code. So this LBB02 label is matched with this jump. And what that's doing is that is what is creating the loop. So remember, for those of you who are really new to assembly language, for loops, while loops, do loops, all of that stuff doesn't actually exist in the processor at all. Those are just shorthand notations for tests and go-tos. So basically, like, you can think of all loops in C as getting rewritten first as an if and a goto, and then they get translated into assembly language, is a good way to think about it because that's what's actually going to happen on the processor. So what you can see here is that's exactly what occurs. This CMP instruction is doing a comparison. It's doing a comparison between a register RAX, which happens to be where we are in our copy, and this value, which is how many things in total it was going to try and copy. I mean, it's not how many things, it's like how many bytes, basically. It was going to copy, and after it does that comparison, it does a jump. And the jump is basically saying, look, if this comparison, it's a JNE, which means jump not equal to, it's basically saying, look, the previous comparison you did is going to set a bit in the processor that says whether or not these things were equal, and then we're going to jump if they're not equal. And so what this does is it says, here is what the compiler did is it pre-computed this value, which is, if we go and actually do the computation ourselves, we should be able to figure it out. We know we have a 4x4 matrix, and each floating point value, in this case, it's a float, so it's going to be 4 bytes long. You can see that that is 64 bytes per identity matrix. And we know that we said we wanted a matrix count of 10 million, right? So if we do 10 million 64-byte matrices, there is our value, right? And lo and behold, that is exactly the value that we're looking at here, right? 000000046, right? So it's this value right here, right? So what Clang did in this case is it multiplied out how many bytes total it was going to be writing, and it just makes RAX be the pointer to the matrix. And you can see here that each time through the loop, it adds 64 bytes, which is the size of exactly one matrix. And so you can infer that this copies one identity matrix to the memory. It advances the pointer by one matrix, tests to see whether it has gotten to the end of the byte range by looking at the total number of bytes it was expecting to write. And if it has reached 0, it will not take this jump. This is jump if not equal to. So, I'm sorry, if it has reached 0. If there's no difference between them, right, then it will just fall through and finish by executing the next loop check, which is this one out here. Otherwise, it will jump back and copy another matrix, right? So again, not very difficult to understand when you actually parse it out. It's just advance the pointer, check to see if it's hit the end of the byte range, and jump back to the beginning. Now, you'll notice that it does take a little bit of work to read this because it's not doing the loop the way we wrote it. We wrote it as going indices of index to matrix count, not index to 64 times matrix count. So we wrote this to copy a matrix at a time, so we use the index of the matrix. But in this case, the compiler, Clang, expanded it out so that actually RAX is a byte pointer. Now, you may ask, why did it do that? And the reason that it did that is just because it's a free transformation for it to do. These are both constants, so it doesn't matter whether this was 1 and this was 10 million, or if it's 64 and 640 million, right? Those are both free, more or less, with the exception of maybe, no, I don't think there's really an exception there. That's just basically just both going to be free. So it's a free transformation to do, and it gets rid of extra addressing that might have to happen in here, or you would have to do RAX times 64. So it's trying to reduce the complexity of the addressing used when it's actually trying to figure out where to write this stuff. So that's a transformation that it probably will usually apply, because why not, right? We need to have like an auto ban of Rust from the chat. Anyway, so if you take a look at this, what you basically find is that this is the part that we probably actually care the most about. I'll speak briefly about what is going on in the assembly language here, just so that everyone's clear on it. When you look at what's going on, these two instructions are usually what are called fused macro ops, or usually are macro ops subject to fusion, might be the way that you would say it. So one of the things that you'll notice, and you see this actually twice already just in this really simple piece of code that we have here is that usually what's going to happen in assembly language is that most of the time you don't just jump around the code for no reason. Most of the time you jump around the code because you've done a comparison and you're trying to skip over an if body, or you're trying to go back to the beginning of a loop, as is the case here. And so almost always you will see a comparison instruction paired with a jump instruction. So what the processor actually does, because this pattern is so common, is that actually comp jump, even though it's not an instruction, is actually what the processor treats it as. So this, on modern x64 processors, will often be interpreted not as two instructions, comp and then jump, but actually as one instruction, which is comp jump. So the reason that's actually important is because when it actually goes to process this, that will often not count against you in your 4 ops per cycle. So on like a Skylake part, for example, which is kind of the most prevalent part right now, although that's going to change because AMD is going to take over the world next year and no one will be using Intel processors anymore because they no longer are able to actually make them. At the moment, when we talk about the most common processor, it's a Skylake processor, and it's going to fuse these into a single operation, which means it won't count against your 4 instructions that you get through the front end. I believe it gets fused and can be put through as a single instruction. And again, when you're trying to look at the throughput of a processor, one of the main things you look at nowadays is what's called IPC, or instructions per clock. And when you talk about the number of instructions per clock that you can actually do in a processor, it's around 4 microops on the Skylake cores, and this is an interesting case where you actually get to fuse those through the entire pipeline, I believe. It's actually macro-op fusion, not micro-op fusion. I believe comp jump actually goes through the entire pipeline as one, meaning it only counts as one in the front end and only counts as one in the back end as well. Don't quote me on that because, again, I'm not an observation guy. It might be that it's only micro-op fusion, which means it actually counts as 2 in the front end for certain parts, and then it counts as 1 on the back end. But either way, point being, these get fused together and don't count against your execution time at all. As 2, they count as 1. And I think part of the reason for that is also that if you think about it, jump isn't really an operation. So comp is something that actually needs to go through an execution port. It actually needs to do work to figure out if these 2 bit patterns are the same. So it's taking actual values, feeding them into an execution port, and actually testing to see if they're the same. Jump doesn't actually do anything. It doesn't have any execution ports. It's just a thing in the front end that says, I need to fetch a different execution set. I'm going to fetch these instructions rather than these instructions as the next things to pull into the out of order window. And so what usually happens on jumps is they're either completely free, as I was saying, meaning the comp is the only thing we actually care about. So the jump is either completely free, or it actually has a branch misprediction penalty if the branch predictor failed to guess which way it would go, and we'd end up spending 20 cycles pulling in the correct instructions because we actually pulled in the wrong set of instructions or something like that, right? So jumps get into branch predictors, not very relevant to this particular thing, but it's because this loop is running so many times that it's always going to predict basically correctly, because it's always going to take this jump, except for the very last time that it runs. And so it really doesn't matter that much to us here, but it's worth understanding what's going on. So what will actually happen at the end of this is we'll have an add on the scalar pipe, because this is a scalar add. We'll have a comp on the same, so this is actually an add and a dependent compare. And then it will do the jump. These can all be, these 2 will issue, like I said, together. For free, you will get the jump. It's only the comp that we're worried about. And the add is actually, again, dependent. So it's going to wait. This comp is going to stall waiting for this add to finish. So it'll be like 1 cycle on the add and then 1 cycle on the comp, right? And the jump is free. So really what we care about is what we're going to start looking at up here, because also typically when you're talking about doing large moves, and you can actually see this happening here, XMM registers are the SIMD registers. They are the wide registers. Typically the pipes are separate. So on Skylake, they're completely separate in the sense that scalar adds and like MOV APS are not on the same execution units at all. This is going to be something that's on a memory execution unit. This is going to be something that's on one of the scalar arithmetic units. And I believe there's slightly different. So it's let's just go full pull on this. I mean, it's a handmade chat after all. So here's our instruction. No, it's just add. Sorry. I'm thinking SSE. I was one step ahead of myself there. Come back. Maybe I'll make, there we go. That's what I need. Okay, yes. All right, so in this case, we've got an add with a 64-bit register and an immediate. So if you take a look at what's going on here, we can actually pick out exactly that one. So you can see here, like, here's an add with an RS64, and it's probably an I8 because it's only adding 64, so it doesn't need very many bits to encode that. Now, I don't know if I can get code bytes on here. It doesn't really matter because they're going to be this pretty much same anyway. But point being, let me open it up. So here's the performance breakdown for Skylake X Core for the add instruction where you're adding an immediate to a register. And it doesn't really matter if we got the right one or not because as long as we're in the ballpark, it should be basically the same. And what you can see here is the port usage here tells us which of the actual execution ports on the Skylake processor are going to be able to use it. And you can see Ice Lake, Canyon Lake, Skylake. We don't have Ice Lake or Canyon Lake. Nobody does because Intel can't figure out how to fab them. So you might have this if you're using like a recent laptop. This, I think, got Deep Sixed. They printed a very small number of these and then they just gave up. So this is the only thing you might have if you have a modern laptop. There are no desktop Ice Lakes, I don't know if they ever got that working. They may never have. So ignore these two because these are not particularly relevant right now for anything, honestly. So we're really looking at this right here. And here's the port usage. Now, the port usage happens to be the same, so we really don't care. But it's worth noting that this is the core that you probably actually have, right? Similarly, this might be the core that you have. This one's a little harder core, so it depends which one you have. This is the one I think is in this machine. I don't think this is Skylake X because Skylake X has AVX512, if I'm not mistaken, and this machine doesn't. So I believe this is just a regular Skylake core. Again, same port usage, so it's okay. And what this P0156 means, that's the list of execution ports. There are like 7, I think, in a Skylake core. 0, 1, 5, and 6 can all do an add, right? And so it takes one cycle, not one cycle. It takes one of these execution ports, and it will do it on any of them that it has. What this means is that if you have 4 add instructions that are all independent, you could actually get them all going on separate ports and not have to wait, right? So in other words, you could issue on port 0 an add, on port 1 an add, a port 5 an add, and port 6 an add. You could issue adds on all 4 ports at once. That's why they end up with a thing that's like the reciprocal throughput here is 0.25. That's basically saying 4 per clock, right? Meaning it only takes a quarter of a clock, quote unquote, to do an add because you can do 4 of them at once. Now, any given one actually will take 1 cycle. That's what this latency tells you. But this thing is just saying, hey, there's 4 ports, so it's effectively 0.25, right? So again, just trying to give you a little bit of a flavor for what's going on here, right? And so basically the CPU resources that are going to get assigned to be doing this, the add can go to any of 4 ports. So what I was trying to get across there is that pretty much no matter what happens in this loop, unless it is absolutely psychotically tightly optimized and can only work with 0156 as its ports, this ad will probably just sneak in there for free, right? The ad comp is probably going to end up being pretty free. Let's look up the comp as well while we're at it. So this is an R64 versus an immediate 64, or that's a 32, right? I think it's a 32-bit immediate, right? It was 640 million, so that's well within the 32-bit range. So let's take a look at this comp of the R64 register, and here it is. The comp can happen on all four as well, right? So chances are this is literally irrelevant to the loop runtime. It will just find a hole. One of those ports will be open, and it will just find a hole and fill it. So we can almost say, I mean, once we look at this, we'll have a better idea of it. I mean, I can already tell just looking at it that it's true. But, I mean, imagine that we had to focus on this a little bit more closely. This will almost certainly just fill up execution port bubbles in our routine, and we just don't have to worry about it, right? So this is basically free, and we'll just find of those ports, 0156, it will just find one to execute on and execute on it in the shadow of all the other crap that we're going to be feeding the processor, right? Okay. So that's what's going on at the end of the loop, and we can more or less ignore it completely. So now what we're looking at is just this. What does this code actually do? And to be completely honest with you, while I think I know what it does, I have literally no idea. Like, I literally have absolutely no idea why the compiler is doing it this way. There's probably an explanation, and if there's someone out there who works on the Clang backend who's watching this, maybe you can tell me what the heck happened here. I don't know. Maybe there is a smart reason why you would do this, but I don't know what happened here. Let me walk you through it. I'm struggling to figure out. I mean, the only thing I can say, because I've never looked at the back end of Clang before, so I don't have an idea of like how it could get itself into this situation. I guess maybe the reason it ended up doing this is because it was penalizing. I'm sorry. I don't know. I have no idea why it's doing this. I wish I knew. I'm sorry. Yeah. I think our only real hope is that somebody who works with the Clang backend is watching the stream and can post later to tell us why, how it got itself in this state. So let me walk you through what it's doing. And I'm sorry, I can't, because that's not my expertise. I don't spend a lot of time looking at the Clang compiler backend. In fact, I don't think I've ever looked at the Clang compiler backend. So I don't know what set of heuristics went wrong to get it into the state, or if this is somehow really brilliant. But my knowledge of Skylake suggests that this is not even remotely good. Maybe it was trying to optimize for another. I don't know if there's a way to basically say like, hey, what would you do if you knew you had a modern? No. So it seems to want to do that, even if I tell it it's a very modern processor. So I'm sorry, I've got nothing. I don't know why Clang did that. It's just seems just kind of nuts to me. So maybe someone else can clarify that later, what the heck it was doing here or why. I don't know, but let me tell you what it's doing, and then we can go from there. So if you take a look, what you've got is you have essentially a set of instructions that are sort of paired a little bit. So you can see that, it's doing this loop where it's going to do 4 separate mobs, right? And those mobs are going to be moving a particular constant value into particular locations. And what you can see is this value is a very specific structured value. It's hard to determine what this actually is for a human because it happens to be a floating point number. Now, remember, we're actually moving this pattern here around. But what we can do in this case potentially is just, if you happen to know what 1.0 looks like in floating point numbers, then you know what it is. But if you don't know, it can be tricky. So I want to show you a little trick so you can figure out what the heck is going on there. If I was to do this, what you can see is that this value now changed, right? So that's a way of me verifying that that number is just the floating point encoding of 1.0 without me having to actually go figure out what the floating point value of 1.0 actually is in binary, right? Is I can just twiddle some of these and see if I'm right, and it turns out, that I am. So this OX3F8 with the zeros at the end is just floating point 1. And what you can see is that it's doing a move, so it's copying memory. It's saying, I want to write a constant, so an immediate value, this value, and I want to write it to RBX plus RAX, right? These are 2 registers. We can infer, I haven't even looked, but I can just infer that RBX is what the base pointer of matrix. So this is what we got from malloc. And in fact, you can see it happening right here. There's the return value of malloc getting copied into RBX. So that's just the base pointer. And then RAX, as we already determined, is just the byte offset of the current matrix we're writing. So you can see we'll do an RBX plus RAX, and we're going to do that. We're going to do these writes throughout. So you can see everything here is like RBX plus RAX, RBX plus RAX. So all of our writes are all just writing to offsets of the actual matrix we're trying to write. Make sense? Like that's what we're doing. And what you can see here is that the actual way that this thing works is completely nuts. It's absolutely bonkers. I never would have thought to try this, and now that I've seen it tried, I have no idea why it was tried. And I can't imagine it's ever a good way to write this loop. But what's happening is it's literally moving the 1 value. So this value, 1, right? It's literally writing the 1 value into the first slot. So the first floating point slot of 32 bits, 4 bytes, it's writing that there with a single 32-bit move. So it's just writing 32 bits or 4 bytes. It's writing it here. Then it is doing this load. So it's doing an XMM word pointer RSP plus 32. Now, what is RSP plus 32 in this case? Well, RSP is usually the stack pointer, so that's usually something that's on the stack. And what is on the stack in this case? Well, you can see right here that what we did is we did an XRPS on XMM0, and XRPS is packed single XOR. It's I have a whole hour left, so I think I'm okay to just be this explicit. XORing your register with itself clears it. That's because XORing any 2 values together that are the same, right? So if I have 2, if my 2 operands to XOR are equal, I get 0. That's because if you do a exclusive OR, it's baked into the name. Exclusive OR means it has to be exclusively ORed. Like it has to be one or the other and never both the same. So 0, 1 produces 1, 1, 0 produces 1, but 0, 0 and 1, 1 both produce 0. That means XORPS of XMM0 with XMM0 will produce 0 everywhere, even no matter what this value is. It can be anything. And this is actually the topic I was starting out with today, which was XOR clears. And we're going to talk about what that does. The problem is the compiler never used them in the loop anyway. But we'll talk about them at the end because I wanted to talk about what they were, and so we'll get there eventually. So this actually clears XMM0, so XMM0 is just 0. And then what the compiler does is it moves to the stack, RSP plus 32, plus 16, and plus 0, 3 copies of 0, right? So it's saying, all right, I want to store 0 to the stack 3 times, right? And again, this is why I don't really understand, like, I'm passing O2 here, and I've passed O3 as well as an attempt. Those are supposed to be optimization flags as far as I know. Maybe I'm just naive with Clang and you have to say something else. But I don't really know. Does anyone know, like, is there anything I can ask this thing to do better than O3? I'll just stop real briefly and ask chat. Does anyone know if Clang does anything more than O3? Anybody? Because as far as I know, that's as optimal as Clang is likely to get. I mean, I can give it, like I said, I can give it the benefit of knowing the architecture is better than the base SSE2, but it doesn't seem to change the code. So as far as I can tell, minus O2 is all it gets, right? Like this is the code no matter what I pass. Right? So, I don't know. So, let me finish explaining what it's doing, and I'll go through all the ways that it's absolutely ridiculous and makes no sense. So, what it's doing is clearing this to 0 and storing it 3 times to the stack. So, it's basically creating 3 places on the stack where it stores XMM0, and that XMM0 is basically just clearing 48 bytes. Right, so there's 48 bytes of 0 on the stack, starting at RSP and ending at RSP plus 48, right? So, because each one of these is storing 16 bytes. Move APS is move aligned for a 16-byte register, right, which is XMM. So clear a 16-byte register, write it to the stack at 3 locations sequentially. So we now have 3 times 16, or 48, contiguous 0 bytes, set that up. And so in here, what it's doing is moving the 1 value, then it is loading into XMM0 what it stored to the stack, which was 0, and coincidentally, it is what XMM0 is. So it's loading XMM0 here in this line, even though XMM0 already is 0. So this line does literally nothing. It's a complete waste of time, but it does it anyway. Then it stores the 0 to the next location. So remember, it wrote 4 bytes. Now it's going to write 16 zeros here. Make sense? Then it does the same thing again. Write the 1, load 0 again, and load it from a different location. Even though these are all the same value, it still decided to load it again, right? From a different location, as if this were different memory. Then it writes it. Then it writes the 1 again. Then it does another load to load the final 0 value, even though the whole time XMM0 was 0. And then it goes ahead and writes the final zeros and the final 1s, right? Does this make sense? You see what I'm saying? I have absolutely no idea why it decided to do that. Someone was saying make it const. The compiler already knows that it's const, right? Nobody else got visibility to this value. So there's no way, like, I don't know. So if adding const helps, that's just a compiler bug. But I'm pretty sure it won't matter because, again, the compiler already knows that it's const, right? So it just doesn't matter, right? I mean, that's not relevant. People always think const helps, and it doesn't, because the compiler either knows it's const already or can't count on it anyway because of constcast. So there's almost never a case where const affects optimization. It's pretty important, right? So you kind of have to understand that like const doesn't usually help optimization almost ever, right? So you can see that this is just really bad code. And if you really wanted Clang to generate this, you would probably try to do stuff to fool it into writing better code, because this code is horrible. How is this code horrible? Well, first of all, it doesn't need, even if you were going to do it this way, where you write a 1, then write 4 zeros, then write a 1, then write 4 zeros, then write a 1, right? None of this code, none of these lines are necessary. XMM0 is already 0. It doesn't need to store it to the stack at all, and it doesn't need to load it from the stack at all. So literally you can just delete these instructions. They don't do anything, right? So that's incredibly bad code. And this is just a bug in the back end as far as I'm concerned. Like that should never have happened, right? Let's see what would happen if we moved these outside of the function. Does it change it at all? So it actually produces better code if you move it outside. So actually, if it doesn't know that it's constant, it produces better code, actually. It's still not necessarily fantastic code, but it's a lot better code, right? Like this is way, way better code. In fact, this may actually be more or less optimal. It's probably as good as the repmov SQ that MSVC was doing. So like, yeah, moving those outside helps a ton, but I'm not done talking about this, so I'm going to leave them on the inside for now, because I want to finish talking about this. So obviously, hopefully, everyone understands why these instructions are ridiculous. They're because it's loading 0 off of 3 locations of the stack, even though it was already 0 and doesn't need to be loaded at all. So even if you wouldn't even have to replace these lines with XOR PS, because you already cleared it. It's already clear. So you don't even need an XOR PS here. You can literally just delete these lines completely. They don't do anything. But even if you deleted those lines, this code is still not very good. And the reason it's not very good is because if we look at what's happening with that code, what we can see is that it's executing. So skip the MOV APSs. Let's assume that we got rid of those and the compiler wasn't quite as dumb as it is. So suppose it just did the MOV and the MOV UPSs. So that's 1, 2, 3, 4, 5, 6, 7, right? So it's requiring 7 instructions to move 64 bytes, right? Seven instructions to move 64 bytes. How many instructions should it take, right? How many instructions should it take to move 64 bytes? Well, if we assume that we're only on an SSE-capable computer, so we don't have AVX, then if we wanted to use move UPS, for example, which is the largest move available on an SSE target machine, move UPS moves 16 bytes. So to write 64 bytes to memory, we should require 4 instructions, 4 move UPSs. If we just did 4 move UPSs, we would write the entire thing. But because it chose to write the 1 as an actual separate scalar move, we're creating 7 instructions where 4 would have been sufficient. Scalar moves and wide moves happen on the same ports. Ports for memory ops are not dependent on whether they're scalar or not in Skylake. So if we pop back to our UOPS table, we can see just how bad this is. So let's go ahead and take a look at a MOV. And what you can see is that if you look at everything that's written here, all of the MOV stuff that we care about is... Where is the MOV that we care about? Oh, right. Never mind. So one of the interesting... I was looking for the R64. This is actually the 32-bit MOV, right? It's going to be a move quad word if it's not. So forget that. There's a little brain fart on my part. So this is the part we're talking about here, right? Oops. I take that back. Where is it? Where's the immediate move? So this is a move immediate to a memory location, right? It's... So I don't know where it is. It may be that it's named differently in here. It may be because these are only micro ops, so it's actually going to do a different one of these. But I don't see any immediates in here. So why can't I get the immediates in here? What am I missing? Do I need to tell it something else? Because it should be in the base instruction set, and there should be a MOV for an immediate. But it doesn't look like there is. So this may be above my pay grade of why the UOPS info table doesn't have MOV on there as MOV. These will be. These are all on here. Where's my SSD? There it is. So these are easy to understand. You can see, and the scalar move is the same. So ports 2 and 3 are the ports on which this can happen. So when you are doing a write, you can see that, like, if you're trying to do a MOV from a register to memory, or from a register to memory, or from memory to a register, you can actually see what's required by looking at the port usage here. What these are, I can't say that I know. Oh, I know what these are. So this must be the nomenclature they give to... So, okay, you can see a register-to-register move is free because it happens in the rename. So these are probably just what the names they gave to those front-end micro-ops. I've never seen that before, so I didn't know these had a name. But it looks like these are synthetic things that the UOPS.info people... I don't know if these are standardized, but these must be synthetic things they gave to basically say, look, this is what the this is what we're calling the micro op that renames, and it's weird to call it a micro op, but it basically says if I have two registers and I want to copy one to another, that's never actually doing an operation. It's just renaming that value by giving it a new name. So now that value has two names in the front end rather than one, right? In the register allocation table. So that's probably what these nomenclatures are. We haven't really gotten to the rat yet, but we'll get there eventually. So these here are the two move UPSs. This one is moving a register into memory. This one is moving a memory into a register. So this is like a load, right? And this is like a store, if that makes sense. And so you can see here the breakdown of ports. You can see that port 4 is necessary for storing. And then ports 2, 3, or 7 can all be used for for address generation. So the thing that actually determines like where this thing's going to get stored. That looks like what it's trying to say here. And unfortunately, I can't seem to load that out of this one. And I don't know why. I don't really know why that is. I should be able to find this here. I mean, this is sort of like what it looks like, right? I mean, this is a move from a register to memory. So you can see it's the same exact breakdown as the MOV here. So it's like writing to memory looks basically exactly the same, but I'm not sure. I've never really looked up the MOVs in this uops.info table, and I have to admit it throws me for a little bit of a loop. These look like exactly what I would expect, except that I didn't know that they gave names to these. This doesn't, and I'm not sure why it seems so limited there, and you know, I would have expected to see other permutations of MOVs, and there might be a reason for that. It might be that there's like some kind of a different name that they give those, and so you don't look them up by the actual assembly language mnemonic. You look it up by something else. And we can look in the Intel Intrinsics Guide. I'm not the Intel Intrinsics Guide, the Intel Programmer's Manual to see what it actually says, because it might guide us a little bit better there. So if I go ahead and pull this up and we look at MOV in here, we can see if there's, yeah, but I mean, even just looking at this, right? Like I was expecting to see MOV Q in there as well, right? And you know, I typed in MOV and it doesn't even have MOV Q in there, which doesn't make a whole lot of sense to me. I guess because it's only in SSE, so that's fine. So maybe that's part of it. Let's see here. No, it's just not there. Well, at least MOVQ is there. I don't know. So let's say we look at MOVQ, right? If we look at MOVQ, that's a 64-bit write. 64-bit load from register to register, right? And so here's one that's like writing 64 bits to memory. And you can see it's the exact same thing. Same port usage. So I don't know why UPS is weird there. If somebody else knows why it doesn't have, like, here's MOV, for example. Here's all the permutations of MOV. There's like a ton of them, right? You can see how many MOVs there are. There's like infinite MOVs. And I don't know why. Like, here's a MOV, for example, that didn't show up in the UOPS table there, right? I mean, so I just don't know. I couldn't say. It might be just because they figure, well, we didn't want to list them all, and we know that it's basically just going to be the same port breakdown as this one is, so just use that one. I don't know. Somebody who works on ups.info maybe can clue us in on what's going on there. All of that, I apologize for wasting so much time on that, but all of that was just to say MOV and MOV APS and MOV UPS, they're all banging on the same ports, right? So it doesn't benefit you at all to insert 32-bit moves in the middle of your 64-bit moves. There's no reason to do so. What's the problem? Oh, do you want me to look at chat? Okay, re-say what the chat is. Oh, was the whole time there was another page? Are you kidding me right now? Where's the... Oh, it's behind my head! I don't feel like that's the Owl of Shame. I couldn't see it. It was behind my head. Oh, no. All right. Thank God. I thought I was losing my mind. I'm like, what is going on? Whew. All right. Thank you, chat. Thank God. All right. So this is what I was expecting to see. I'm like, God. I even thought in my head, I'm like, haven't I ever looked at this in UPS? I'm like, maybe I haven't because it's just kind of obvious, so I wouldn't bother. I mean, I don't know. Okay, thank God. So finally, this is what I wanted. These are what I wanted. So this is moving immediate, 32-bit immediate to a memory location, right? So we can find that one on here, and this is it, right? This is, oh no, sorry. This is it right here, right? 32-bit immediate moves to a 30-bit memory location, and you can see that the ports are 237 plus 1 P4, right? So it's going to take 2 micro-ops. One is P37. I believe that first micro-op is the address generation. So basically what that is this thing. It's taking this RBX plus RAX and turning it into an actual like location that it's going to write to, right? And then the 1 times P4, P4 is the write port. So that's the execution port to actually, like, once you have an address and you have a value, it's going to put it out there, right? Make sense? So just so you know, that's what's actually going on there, right? Okay. Whew. I'm glad I wasn't crazy because I'm like, what the heck? I'm like, where's all the mobs? There's so many of them. All right. So as you can see, this is all going to hammer on the exact same port. So this is just a disaster. This loop is crazy slow for no reason. It should just be 4 move UPSs because all it really needs to do is have XMM 0, 1, 2, and 3, have 100, 0100, 0010, and 0001, and just write, right? So if we want to help out Clang and say, hey, Clang, I know it's been a bad day, right? In fact, I guess I'll just do it this way to avoid confusion. I'm just going to say, look, let's help you out here. Let's tell you what is going on because you obviously don't know and are very confused about the world. Let's create 3 explicit register values that you can use, like so. And then let's tell you how to actually do your job. So let's do a, you know what? I'll just put a little if 0 in here. So we'll get rid of this write. Like so. And I'm just going to try to store the rows myself. Right? So you can see me trying to store 1 row there, and I just want to store all 4 rows like so. And here is the new code that basically says, all right, I'm going to generate, hopefully, 4 registers, XMM 0, 1, 2, 3 or something, right? Each register will be set to 1 row of the matrix. And I believe set RPS is the way that you say that you want to go in memory order. Let me just make sure that's true. Before I lead everyone down a bum path there. Oh, no, it's not. Okay, so it is normally memory order. Is that right? I almost never use these functions directly. I always have them like written in my own version. So no, that's not it. So set PS. Oh, no, it is. It is. Because they're in opposite order in the parameters. So yeah, it's set RPS if we want them in memory order, which is what I wanted. So here's them set to the various rows of the matrix. So we're not going to use this. We're just going to set these up directly so the compiler understands what they are. And then we've got this storing here. We're going to store each row of the matrix as written, right? And then I'm going to see if that helps this thing out at all. I don't know if it will or if it won't, but we'll see. And lo and behold, yes, it does. So if you look at what actually happens with this piece of code, it actually has produced exactly the right code now. And if you're wondering why there's 8 stores instead of 4, it's because it chose to unroll this loop 1 time. Why it chose to unroll this loop 1 time? I don't know why it chose to unroll the loop. That may be because it's thinking of a broad set of architectures. So when you issue, because this is free, so the subcomp jump is going to snuggle up in here and just be executed in parallel with this. There's no way to issue 4 stores per cycle. You can only issue 2 stores per cycle at most. So the fact that this is dependent, the subcomp jump, it should just nestle correctly where it will do, if you had just had 4, it would do the sub with the first one and the comp with the next one, and then it would go to the next part of the loop. I don't actually know if there would be any value at all to unrolling this loop. I can't say that I would expect there to be. So why the heuristics told it to do that? It may be because it's thinking about more architectures than I am, so it's maybe like broader. It certainly can't hurt. It's not really like gonna ruin anything that it chose to do that. So like, I mean, I wish I had an explanation here for that, but I don't. I really don't know. And you can see that there's issues that it's created. So the fact that it chose to do this means it had to do a little bit more fancy footwork here than if it had just done what I told it to do. And I think what I told it to do is honestly still better. So I still think Clang is kind of wearing a slight dunce cap here, but I don't know. Like, there may be some reasons to unroll this, so I'm not going to criticize it, because maybe that's actually smart on some architectures and so on. Like, maybe that's a good thing. So, but point being, now you can see we've got it much cleaner. This is probably twice as fast as the other loop was, because rather than doing 7 instructions, it's doing 4 instructions per matrix. 4 instructions per matrix is almost twice as fast as 7 instructions per matrix. That's just kind of how that goes. So there you go. Yeah, and anyone who thinks that like the O3 helped, it didn't. We can put O3 on now to see if it changes, but it didn't seem to change at all what we were doing. We can leave it on, though. There's no reason to have it not on there, but it basically does the same thing. So that's at least sane. And this is also why I tend to write things out explicitly as often as I can, because compilers just aren't very good. A lot of people think compilers are smarter than they are. They're not. That argument's been had on Twitter before, and the people who say the compiler is smarter than a programmer must be talking about other programmers, because I come across this sort of thing all the time. And that previous loop, I will absolutely stake my reputation on using 7 cycles to set 64 bytes is just plain dumb. Again, I am no optimization god, and you shouldn't take my word for anything optimization related, but that one is pretty blatant, and I will be shocked if someone can point to me to something that suggests that doing that 7 cycle sequence was better than doing 4 MOV UPSs. I will be very shocked. Anyway, getting back to what was happening here, if we switch back to the other version really quickly, I wanted to point out briefly what MSVC was doing here and why I thought this was particularly cool. So basically, there's a thing built into Intel processors called the rep instruction, and it's kind of a really neat instruction. It basically says, hey, I'm going to be doing a dumb, simple loop. Either I'm going to write the same thing a lot, or I'm going to copy the same thing a lot. Why don't you just do that for me? And one of the nice things that's happened is as the Intel processors have gotten more advanced, their ability to do high performance reps has gone up. So nowadays, calling a rep instruction is actually really, really fast. And you know that you're going to get really good throughput on it because it will be smart and use large block moves where it can. So actually, even though this kind of looks like stupider code, it's just calling some processor instruction rep, and sometimes rep gets a bad name. On modern like Skylake cores, actually rep is a pretty darn good instruction. And so if we look at the uops.info for rep, for example, here is, this is an SQ, right? So I don't know how to ask. I've never looked up this on I've never looked up a rep mov. So I'm not sure which one this would be closest to. Because because I'm not sure which of these would map to a rep mov SQ. This is just my naivete with rep mobs. Let's pick one. This would just be the bite one probably, right? So if you take a look here at doing this on Skylake, here you can see. So you can see like the cost of the ports, and it's pretty confusing, right? Because the problem is it's a loop, so it's pretty hard to determine like what the heck is going on in here when you look at the actual port usage of it. It's just like, well, it's going to use 1 on this, going to use 16 on this, going to use 2 on this, 22 on, like, this is just, I don't know, right? But in terms of the actual cost of the UOPs, for a given size, where the size gets put, the way that you use this instruction is you put the size in one register and like the value you want to move in the other register, or you set up pointers and so on. When you actually do this rep instruction here, it actually is very fast per loop. It basically will do the equivalent most of the time on a modern core, at least as far as I know, of what I did. So this rep mov SQ will actually use the 2 ports to actually do 2 stores per cycle, as far as I know, right? And so this is actually probably way better code than Clang generated when we didn't help it. Once we help Clang and we get here, I think these 2 would be about equivalent. But again, hard to say. You'd have to time them and find out. All right. So finally, let's get back to the thing we actually wanted to know. So after all that, I hope you understand this assembly at least a little bit. What I want to do now is I want to try to actually determine what will happen if we now do some kind of, say, dependent clear. So let's say we stop doing things the way that it was done before, because none of this stuff is good. And this is, by the way, why I was trying to on Twitter tell Jesse to not do things the way he was doing it, is because when I saw the assembly language code that he'd posted, I was like, Clang is doing garbage here. That's what I was trying to say. And I thought it was just because he was compiling with -OG. But actually, now that we've looked at it compile with O3, it's just Clang is just bad at this. It's just producing bum code. So you don't want to do timings with bum code. You got to look and see if the compiler generated something usable to begin with before you actually time it, because that code that Clang generated was so bad that it's not a fair comparison of what would happen if you clear registers. Of course, clearing the registers will probably be free because Clang created a loop that's so slow that you won't notice, right? So yes, clearing registers happens to be free, but that was not a fair test of it, right? So anyway, that's what I was trying to say. Hopefully, that's what you get, right? So anyway, someone wants me to try one more set of compile switches. So before I get rid of it, we'll just try one more to see if it creates anything. You wanted March Skylake, so it knows it's using a Skylake architecture, and fast math. Yeah, I mean, trust me, this doesn't look like any kind of thing that has to do with any of that. It's just super confused, right? And so really, the thing that's confusing it is that for some reason, the fact that this is on the stack, I guess, confuses it, because moving these to actual stored data, it suddenly knows more what to do. Oops. What just happened? Okay, there we go. Moving it outside, it suddenly knows what to do, right? This is, again, just an unrolled version of this loop that's not horrible, right? It's not good, but it's not horrible, right? Actually, it is kind of horrible. Never mind. It just doesn't know. Clang sucks at this. Let's just stop talking about switches. Clang sucks at this. You shouldn't have to set any switches other than optimize to get this to work properly. The compiler has all the information it needs. It does not need const here, and even if we said it, it didn't help anyway. It does not need them to be static. This is obvious. The compiler should be able to figure it out, and it doesn't. That's pretty much period. We're done playing with switches. Okay? No, you cannot leave it inside and set it to static. If you leave it inside and set it to static, right, you're going to get initialization garbage in there, right? I mean, maybe you can. But I would worry, right? In this particular case, oh my God. What the heck did it do? That's even nuts. Yeah, don't do that. Holy cow. That's horrible. All right. Clang is nuts, okay? Just it's nuts. You got to write the code yourself. That's what we did. Just stop telling me switches. Switches, if the compiler was any good, you wouldn't have to know what switches to get it to output an obvious copy from register, right? So it's got a lot of issues. Like I said, this is what I find a lot of times I compile with Clang. MSVC outputs something sane, Clang outputs something ridiculous, and I have to handhold it like this. That's just what I see a lot of the time, and that's what we saw here. Your mileage may vary. Moving on. So let's suppose that we actually want to do what we were talking about at the beginning, which is we want to have some way of doing a potential clear. So we want to see what happens if it costs us anything in the kind of case that involves clearing registers. So in here, let's suppose we move these into place. And so we've got a thing where we set them up and then we write them out, right? And so in here, we've got the same loop, right? This is fine. It's unrolled for no reason whatsoever, but it's, it's fine. It's not ridiculous. But now what I want to do is I want to say, look, if every so often, like maybe if, let's see, maybe we introduce an maybe I try to do something like this. So I say, look, if index equals run, then it's this. And if it's not, it's going to be 0. And all I'm trying to do here is simulate the case where we have something to test, where we set the matrix to the identity sometimes, but we set it to 0 other times, right? So in this case, sorry, I'm not very good with this web editor, so I'm kind of like ham-fisted when I'm editing things because it's not, my normal editor config or whatever, but I'm working on it. I'm getting there, right? So let's say we have something like this, and we take a look at what we end up with in here when we ask Clang to do optimizations on this thing. So here what we're saying is, look, we're going to set these to 0, and then sometimes, right, we're going to set it to the identity. And either way, we're writing a matrix, but sometimes we're going to write the 0 matrix, in fact, most of the time, and other times we're going to write, ooh. I didn't mean to do that. I guess I just saved a copy of that somewhere. So anyway, taking a look at what goes on in this particular piece of code, you can see in here, if we want to look at the stuff that it did here, it looks like it went, again, ahead and kind of went into a rather absurd way of breaking this down. I'm wondering if what it tried to do is outsmart us because you can see these. Let me see if I can make it even harder for it in this case. So I'm trying to think of a way to make this something the compiler doesn't understand. You know what's a good way to do that? Here. So now we just have a function foo, right? And I'm going to make it read out of this control structure so that the compiler doesn't know at all what it has to do, right? So it has no idea whether it's going to do one or the other, and we'll see what it actually outputs here, right? So if you take a look at what it generated for the loop, here's us doing the right. Here's us doing the add, so we're moving forwards, right? Here's us doing the comp and the jump, and we jump back to 11, which is here. And then what we do is we kind of do like jumps around kind of nonsense-wise. So here's us... Oh, wait. No, that's jumping out. So this is the part. So we fall through here. We jump to 2. We do a test of this. We do the XORs if necessary. Otherwise, we jump to... and then we jump to 3. No, we just jump based on the comp. So we XOR some. We jump based on the comp. What is the point of this? Look at how many jumps this thing inserted in here. What did MSVC do? Hold on a second if I see if MSVC is at all sane. So here's the comp. Here's the 0 clear, right? Here's the jump over the... yeah, so like once again, Visual Studio does like exactly the right code, and Clang is a friggin' nightmare. I don't know why I can't imagine having this many jumps in here could ever be good for anything. They're conditional jumps. So these go through the branch predictor even. Yeah, I mean that's the loop, right? It's perfect. It's exactly what you want. You comp, clear, jump if you're not going to overwrite, copy. It's exactly right. So MSVC output the exact right loop. Clang output an absolute monstrosity. I can't imagine that's ever faster. Let's see if O2 was more sane. It's not. What is going on? I just don't know why you'd ever want any of this. This just looks like massive branch prediction nightmare, right? So I want to say, and I could be wrong about this, I want to say that there's some really, really, really bad aspects to this code. So looking at this code, I could be wrong about this, but this looks like code that is absolutely abhorrently bad. And maybe this is, again, just my naivete with optimization. But when I look at this code, the first thing, pun intended, that jumps out at me is that, if I'm not mistaken, at least on Zen 2, which is like one of the highest performance CPUs currently in existence, if you have multiple jumps per 64-byte block of code, every jump past the second jump becomes worse. So like if this is probably like one 64-byte block of code, and there's like 1, 2, 3, 4, 5, 6 jumps in it, right? One of them's a straight up jump, but so maybe that doesn't matter, but these are all conditional jumps. So that many conditional jumps in one 64-byte block is an absolute nightmare for the branch predictor, I think. I mean, I could be wrong about that, but that just seems really bad. Really, really, really not good. Now, again, some optimization, like if Agner Fogg's up on here and wants to tell me that that's not true, that would be cool. But this just looks like garbage. This looks like exactly the right code to me. And so what you can see here is what I finally wanted to get to. And it's not quite exactly what I wanted, because I wanted XOR PS for an XOR clear, but these are actually functionally the same thing. So we can talk about that, and this is what I actually wanted to get to by the end of the show, and hey, thankfully we did get to it by the end of the show. So let's finally talk about XOR clears. And someone mentioned there's a tuning parameter for Zen, so let's see if it knows about that. Nope. I mean, it looks a little better, but it's still outputting a heck of a lot of jumps. I think it may have improved slightly, but I don't know. Yeah, I don't know. Real bad code. So yeah, not great. And like I said, I do feel like my experience with Clang is it outputs really stupid code a lot of the time. But like I said before, I also find that in certain places where it really counts, like in really intrinsic, heavy, like crazy math code, I feel like when I've done Clang compiles, it actually produces the faster code. And so I do think that there are important things Clang does that oftentimes you run it on your whole code base, you actually get a win from Clang. But it's like, I don't know why it's doing these stupid things. It don't seem right. Anyway, so let's talk about this because this is the code I actually want to talk about, and this looks about right to me. So what's happening in this loop is it's doing a comp on the control, right? That's just seeing whether or not it needs to write an identity or a 0. It has mov APSs to move XMM0 into 1, 2, 3, and 4. XMM0 is just the 0 value. You can see that it was cleared up here. So that's just setting these all to 0. Then it's going to just jump over the actual load of the identity matrix. So this will load the identity matrix in. Then it does the same set of mobs, 1, 2, 3, and 4, out to the matrix, right? And advances. Again, exactly what we want. This looks great, right? And so now let's get to the part that I was trying to explain before, which is why I was saying usually clearing to 0 is free. And in this case, you can see why it's free. Because this piece of code, right, doesn't do anything. Mov APS XMM1, XMM0 here is actually not going to ever go to an execution port at all. It's just going to rename the value that was in XMM0 to also be the value that's in XMM1. Modern processors don't have registers the way that old school processors did. When we say that there's XMM0 through XMM7 or something, there aren't actually 8 physical registers in the CPU, each holding 16 bytes. That's not what happens. What there actually is a much larger register table with lots of 16-byte spaces in it for values. And then there are 8 tags, XMM0 through XMM7, that can tag those values. So all that's happening whenever you see a register-to-register move is it's just taking the tag for XMM1 and attaching it to the value that is XMM0 so that now that value is tagged as both XMM0 and XMM1. So anyone who reads from XMM0 or XMM1 in the future will get the same value out of that table, right? It doesn't ever actually copy it to the best of my knowledge, right? So what happens is all of these, the only cost that you pay for them at all is just the decode code space cost, right? So those instructions still have to move through the front end, like they do take up some time to decode in the first place, but for a loop, it's all in the hot cache anyway, and it's probably actually in the loop cache anyway. So these are effectively free. They take no execution ports whatsoever. They only take front-end time. So the only time you could ever pay for a MOV APS or equivalently an XOR PS is the same thing. It's just re-tagging a location as 0, basically. It's processed in the front end. The only time you can ever pay for those in an actual execution cost is 2 cases that I know of. One is when you are actually decode bound. So like the front end is actually the thing that is stalling your routine. In our case, we know that's not possible. How do we know? Because we know we only have 2 possible stores we can do per cycle. There's no way on anything on Skylake that I've ever heard of that can ever store more than 2 stores per cycle. So if you can only do 2 stores per cycle at an absolute maximum, I want to say, I think you can, I don't even know if you can do 2. You may only be able to do 1 store per cycle on Skylake. We should look that up. But point being, I think you maybe do 2 reads and 1 write. I don't know if you can do 2 writes. You can definitely do 2 reads per cycle. But writes, I think, is only 1. Don't quote me on that. But that's my feeling, is that you can only actually do 1 write per cycle, maybe. Either way. It's either 1 or 2, depending on whether it's reads or writes and depending on whether my memory is bad or good. But the front end can process 4 cycles at a time. 4 instructions at a time, right? And since MOV APS is not a complex instruction, it doesn't generate like lots and lots of UOPs or anything. There's no chance that we're going to be stalled on decoding anything. There's going to be lots of spare decoder bandwidth here because we're simply going to be mostly waiting around for the store port to become available. Because chances are we're only going to be issuing like 1 store or 2 stores per cycle. And if we're doing 2 stores per cycle, then we actually have 2 spare instructions that we can issue every cycle in that shadow that it doesn't matter. So the front end, we're not counting on the front end pushing 5 or 6 if they're fused. 4 or 5 if they're fused ops through to the execution ports, because the execution ports are what we're going to be bound on, right? And you'll forgive me for not remembering whether it's 1 or 2, but we can look it up. Chat is saying maybe someone looked up Skylake and it's only 1. So I'm not wrong in remembering that it's 2 reads and 1 write, I guess. But I might be wrong. Either way, it's definitely not more than 2. As far as memory ops, it's either 2 reads and 1 write or 2 reads and 2 writes, but I'm pretty sure it's like 2 reads and 1 write. And the fact that when we looked it up on us.info, it said port 4. It didn't say like port 4 and something else. So if you could do 2 per cycle, it should have said port like 3 and 4, right? So I'm pretty sure that it basically is like, reads on ports 2 and 3 and writes on port 4 or something, right? So you only have 1 port for writes. You know what I'm saying? Anyway. So these are effectively free in almost everything you do, and the reason for that is because it's so cheap to rename things compared to everything else you're doing that you have to have gotten down to like an incredibly highly optimized, really well-working system before they actually pay for them. Now, there is one other case where they could have an effect, and that's code size, or like if the alignment is slightly different. There's all these weird like edge cases you can hit. So I don't want to say that like inserting MOV APSs into something that move from register to register never affects the performance, because sometimes it actually can in a weird way, but that's true of every instruction that you could do. So that's kind of not something you actually are talking about when you're talking about how much does it generally cost to do a thing, because that's like finicky stuff that may have nothing to do with like what the actual cost of doing the thing. So MOV APS and XOR PS in these ways, where you just use an XOR PS to clear a register or use MOV APS to move one register to another register, you're not paying for that. It's not actually bit work being done by the processor in the back end on an execution port. It's actually just happening in the register allocation table, and all you're doing is renaming something. You're either, or clearing. Like you're either saying, oh, there's no value in here anymore, it's 0, or you're saying this value that previously existed is now also called some other register name, right? And so that's why I say for ZII patterns, clearing to 0 is almost always free. You really don't have to do this. This is what you do when you don't ZII, right? When you say, "Oh, I'm optimizing my code," right, by doing this so that actually that's not what I meant to do. You know, people will often be like, "Oh, I'm optimizing my code by doing this," but you're not optimizing your code by doing this, right? This doesn't actually do anything other than introduce a potentially unnecessary operation into the code, depending on how complicated the code gets. In this particular case, the code's so simple that basically these two things will evaluate to effectively the same thing, right? Oh no, you know, it's worse. There's an extra jump, so I'm right. Even in this case, it's true. I was assuming the compiler would be smart enough not to do that, but it looks like it's not. So what you can see here is actually this just introduced an extra jump. Now, it's not technically worse code necessarily because this jump is probably free because it's not conditional. So the front end is just going to eat it and it's probably fine, right? So this is probably not necessary to worry about. But what you can see is you basically just ended up with exactly the same code anyway. These are just clears, so they don't cost you anything. These are the things that you are now doing a jump around, right? So it reorganized the code slightly, but it's basically the exact same thing. So you haven't ended up with more optimal code at all. It's either the same code, or if something was going on here that was more complicated, the compiler may not have been able to figure out exactly what it should have done, and it actually would have just gotten worse, right? So this is like an old way of thinking about things. When you think about having to do this, you're kind of thinking about stuff that's like a decade old or more, right? This didn't change. This is a better way to write this code is to just not do that, right? Is to get rid of this and just always clear to 0 because there's no reason to actually make the compiler think about going down two different branches because you really only ever have one thing you might need to do. If you can start with 0, that's just a way to have the front end eat the clear for free so you don't pay for it, and then you have one branch to avoid overwriting your cleared values, but that's all you actually need to do, right? Now, this actually gets a little more complicated because you can actually make this even more free than that. So you can write this in a way that's actually branchless if you want to. And you can see, like, for example, just to finish off, this is actually just a value we could just use, right? So if we wanted to, we could actually just have a blend here where we actually never do an if. So if we're concerned about the branch predictor getting confused about this, we can actually just eliminate it entirely. And so this is yet another reason why clear to 0 is often pretty reasonable to do, because oftentimes what you're actually going to do in here is you're actually going to do something more like this. So like, this is a totally common pattern that you might see, right? Where I'm now going to do effectively exactly the same code. I think I have to tell it now that we have SSE4. Is it SSE4 or SSSE4? There's weird, what's the name of that thing? How do I get, is it just blend? I may need to tell it, sometimes it's this kind of nonsense. What is the actual thing that needs to be on here? You know what? Forget it. I'll just do it old school. So suppose I want to write this thing out, and I want to just make it dependent. What I can do is just do it by like doing an and not, right? So suppose I just make a macro here that's for blending, so I don't have to type it 4 times. And I just want to blend this based on a value that I load out of the control. So what I want to do is I'm doing the same exact loop. I want to take this control value here, and what I want to do is just use that control value as a mask, right? So let's suppose that I just have a set of masks in here. Maybe these, I want them to actually be like set up properly. I mean, I don't know. You probably would do an expansion here, but just to keep the code as simple as possible. Let's say we're loading the mask out of here rather than lofting it up. Although we can show how to do the control. I'm just trying to keep it simple because we're at the end of the time period here. But so let's say we do a blend here, and so we're going to do a blend of 0, and if the mask is true, we're going to use this secondary value here, right? So then what I do is just say, okay, let's take blend, and maybe I can help fix this here. So here's my various options that I have. And what you can see here is I'm going to load out a control word here. And that control word is I'm going to say is pre-expanded, so I don't have to do it. But we'll actually do the expansion if we have time in a second, so that it can still come from a char. And then what I'm going to do is I'm just going to define a blend macro here, where we basically say, look, I've got an A and a B and a mask value. And what I want to do is I want to combine the two. So what I want to do here is I want to basically OR these two together. There is an actual blend command, but it only got introduced in like SSE 4. So I'm not calling the blend directly because of that. That's the only reason. So if I want to OR these two together, I'm going to OR together an and an and not. And it doesn't actually matter which one's which in this case. Let's just say we're going to and with M and not with the other one. I always have to look up and not because I always forget which one gets knotted in the Intel syntax. So I always look it up and see which one it is. So compute the bitwise not of package transformation A. So the first parameter is the one that actually gets knotted, right? So the M comes first, which is what I did. So I happened to guess right that time, but I usually have to look. So in this case, I think I'm going to say, I think I said A is the one that happens if the not is false. So I'm gonna switch it that way. So we knot the mask for A, and then we use the mask for B. There's our blend instruction. So what that does is just takes the mask and picks A or B based on whether the mask is ones or zeros, right? So now what we can do is we can take a look at the code that's generated, and I'm going to just look at the code on the MSVC side because it tends to be the one that's less ridiculous. And so let's take a look at where this code ended up, right? So here's us moving the control word in. I'll be honest, I don't really know why it's bothering to do these RCX loads from... I have to stop and decrypt that. My assembly language reading skills are not fast enough to know exactly why those LEAs are there. Because it looks like it's just using... It looks like it's just using those as a way to advance the pointers. Which I guess... Anyway, let's not care about that. Let's just ignore that right now. So what this is doing here, right, because that's load effective address. So yeah, just ignore those two for now because those are like working with the pointers. So let's just look at what we did with the UPS. So first what we do here, right, is we load in, excuse me, we load in the control word. That's coming from RCX, right? We then basically take XMM3, which presumably is prepped somewhere here. Yeah. So we take XMM3, which is prepped with 1, right? And we load that into 0. We then we then and that, which is exactly what we would expect to do. We then move, this is, I assume, is 0. We move that into here. So again, these two are both free. And we then and it with 2. We do all of the ands with 2, actually. And then we do, So, wow. Actually, if you look at what this generated, it was smart enough to know that it didn't have to do the blend with 0. Right? So it's not ever even doing the OR because it's just smart enough to know that. So let's, since we were just doing this as a test, let's just make sure that you can see the whole code path. This way it has to actually do something. That was pretty cool though, right? Good job, MSVC. It noticed that as an OR was 0, but there, now you can see the ORs. So it's just going to load those in, and by load, it's actually just renaming the registers, which is great. So it's really costing us nothing. It's just doing an and, an or, and or, and or, and or, right? It's just doing ands and ors. And there's those and nots as well, right? There should be more of them than that, shouldn't there? No, there shouldn't, because these are all the same value. The compiler is so quick, isn't it? It's really doing a good job with the sub-expression elimination there, right? So you know what I'll do? Here we go. There you go. So here you can see the full case where it has to do an and not, and an or for each one. Now again, this may look like a lot of code, right? Because it looks like a lot more code than the other one, which just had one, 4 and then a branch and 4. But what you have to remember is that this now has no branches at all. This entire loop executes branch free. And all of these things execute together. Or and are simple one-cycle instructions for which there are many ports. 3 ports at least, most of the time. And so all of this stuff will overlap. So actually, when you actually profile this routine may be way faster than the other one, depending on the circumstances, because now there can never be a mispredicted branch. So whether this routine or the other one was faster would depend on how random the control word was, basically, right? Now again, we can also amplify the control word if we only want to load 1 byte out. We can always do a load and a shuff to blow that out. But there you go. Okay, so I think I covered everything I wanted to cover. Let's go to a quick Q&A if anyone has any questions. And this is Jesse, whose original post on Twitter motivated this. He says, thank you so much for taking the time to explain and demonstrate this on Handmade Hero. Deeply appreciated. My pleasure. Thank you for taking it seriously. Of everything I saw on that Twitter thread, which was mostly just people making stuff up that they didn't know about, you actually took the time to write some actual code and learn from it. And that is so important. So that was why I did this, because I was like, somebody actually cares rather than just saying stuff on Twitter. And when somebody actually cares, that is the person that deserves to have their concerns legitimated and explored. So thank you for taking it seriously and posting on Twitter. And I'm glad that you found this useful if you found it useful. So yeah. And yeah, the LEA, so load effective address, so because I don't really do much assembly language programming except with SIMD, a lot of the vagaries of x64 or x86 for that matter, assembly language, like using load effective address to do arithmetic and stuff, are lost on me because I never write that code really, right? I'm usually just trying to look at how to make sure this sort of stuff works out okay. So I have a pretty good understanding of how to make sure all of the SIMD unit stuff lines up properly, but like the cool tricks and stuff that's like using load effective address to do pointer arithmetic faster than maybe you could do it with something else. I just don't understand that stuff. I'm sure it's not that complicated. If you went and looked, it's probably not that hard to learn, but I've never done it. And so I don't feel comfortable explaining anything. That may actually be slower than doing the equivalent now, and it may be kind of antiquated that it's doing that, or it may be that that's still the best way to do it. I have no idea, so someone else will have to talk about that. I compiled the code with ICC, the Intel compiler, with O2, and it takes 3.5 seconds to run it. Is it really bad? Well, it depends on what the platform is. I don't know. And again, like I don't really have a feel for how fast this thing should go yet because we haven't tried test running it or anything. I will say that the memory bandwidth on your machine will make a big difference because this is going to be out of the cache. So if you look at how many bytes that is, this is the total number of bytes, right? So it's 64000000 is the number of bytes that it's going to have to write if we did that correctly. So if you take a look at the cache size or typical cache size that you might find on one of these processors, you're going to find that like 256K is like a typical L2 cache size, for example. And so this is like way more times than the cache is covered. So you're looking at L3 or main memory bandwidth most of the time. That's actually going to be a big bottleneck. So one of the reasons that if we were actually going to move into like actually talking about this and testing this in a real scenario, rather than just talking about what's happening in the registers for educational purposes, we would have to acknowledge the fact that the amount of memory that this thing is working with at a time will make it very difficult to assess differences in the routine in the first place, because there's so much memory getting touched here that the CPU's memory bandwidth will really be the bottleneck. Because remember when I said it can do 2 stores per cycle, that's 2 stores to the L1 or the L2. There's no way it's going to get 2 stores per cycle to main memory because main memory isn't fast enough for that, right? So you have to keep in mind the performance overhead of stores is 1 cycle to L1 and 14 cycles to L2 typically. So depending on exactly what you're doing, you may be able to get L1 or L2 bandwidth, which may end up equating to something like 1 store per cycle. Sorry if I said 2 store cycle. 1 store per cycle to L1. You're going to get 1 store every 14 cycles to L2, and you're going to get 1 store very much less frequently than that if you have to go L3 to main memory, right? So the fact that we're doing such a huge chunk of this thing, this is not indicative of how you're usually using clear to zero. Normally you're talking about something local that you're about to use, like I'm initializing like an entity or something. And those are the cases where clear to zero is completely free usually because you're about to use it anyway. And you can go as fast as L1 goes because you're all in the L1 doing stuff in the L1. When you're talking about giant clears or giant writes, usually it doesn't matter what you do because memory bandwidth is so slow, you can do several instructions that are irrelevant and don't matter. Even the branch misprediction penalty probably doesn't matter because it's on the order of 20 cycles and main memory bandwidth is on the order of like 100 cycles or something. So it's just worth noting that these are the limitations, right? Someone has mentioned that older versions of Clang generate better code. It could be, right? Performance regressions are real. And their test suite probably can't capture everything. So, if we go back to doing this thing, which was where it was kind of generating really bad code, if I remember correctly. We can certainly roll back. So let's suppose we roll back to like an earlier version of Clang. Let's say Clang 7. Looks the same. We can roll back to 4. Looks the same. So for whatever reason, like Clang's memory analysis here is it just rolls over and dies. Who knows why? Just hit a bad case, I guess. I don't know. I read that mixing SSE2 and AVX2 will incur a performance penalty. How would you handle optimizing code if you want to support AVX2 but also SSE for older systems? Would you just have separate builds for each? So let me first take a moment to cast a slight shadow of doubt on that statement. I don't actually know that it's fair to say that mixing SSE and AVX2 code incurs a performance penalty, because it does. I mean, that's not wrong. But it's more precise to say that mixing V prefix and non-V prefix instructions can have a performance penalty. So AVX instructions are prefixed with V, but so are SSE instructions written in AVX. So the SSE instructions themselves have V prefix versions that you can use, and you see them show up. So here's the exact same code when I say MAVX. It'll all have V prefixes inserted in front of it. So the code is actually completely the same. The only difference is now it has a V prefix. And that's to avoid calling V and non-V instructions in the same path. Whether that has a performance, so calling a V and a non-V in the same path, whether that has a performance implication, I think depends entirely on the architecture. I don't think it's true for all architectures, but I could be wrong about that, right? And to the extent that you care about this, what I would say is, typically what I do is I isolate all of the code that is architecture dependent into like one file. I usually call that like x64 underscore, math or something, right? And then I will have variants of it. So in that file, I will have if blocks determining which one I'm using, or I will just have like AVX underscore AVX2 underscore SSE underscore as my files, and then pound include if 0 around which ones I'm going to include, right? And I will just create the code for each path. I will write the entire path that way. So I'll compile all of my SSE routines as AVX routines and so forth. Switching between, so if you just have the compiler outputting SSE instructions in your normal code, and then you call into an AVX routine that's going to have V prefix instructions, I don't think that performance penalty is going to hurt you, because it's only the first time you do it that you pay a transition penalty, and it's not that expensive. So the only thing you're really trying to avoid there is like inside a loop. You don't want them both. But like if you occasionally switch between the two, I don't think it's going to matter. That said, allowing the compiler the ability to generate AVX code is usually kind of good. So what you might want to do is just have two builds of your game and just have a little shim that starts up and loads the right one, right? So like build 2 DLLs, AVX, AVX2, or 3 DLLs, SSE2, AVX, and AVX2, or something like that. Or AVX 512 if you're really gung-ho. And then just load the right one, or load them in series and wait for them to fault and then switch to another one, whatever you want to do, right? Someone asked if we could show what GCC does. Yes, we can. Where is it, though? Here it is. So, wow. All right. Is that really what it does? So GCC's code is terrible. It did the entire thing with scalar moves. Try Clang 6. Still looks bad. Clang 6 looks wrong, doesn't it? Still? Still looks bad. Okay. So O3 made a big difference for GCC, though, right? That is the correct code. So GCC absolutely trounces Clang here at O3, for what it's worth. Could you provide the Twitter conversation link that you are responding to for the YouTube video? I thought I did, actually, at the beginning of it. But it was Jesse Meyer posting some tests he was trying to do right here. This is what I said, because, like I said, I appreciated the fact that he took the time to do this. So I wanted to take the time to expound on it. And just say my thoughts on this particular topic. Latest Clang with well, I thought I did. I think we did try the latest Clang with O3. And yeah, that's latest Clang with O3. So let me pause for a second and also say one more thing before we conclude. This isn't a tractable situation, right? This is like really bad. The fact that everyone's like, try Clang 6 with O3 and arch this. And it should produce reliable code for reliably written, simple pieces of code without having to be some kind of a switch jockey. Now, in this case, it never produces good code. So Clang, as far as I can tell, will never produce good code for this, period. But this is one of the reasons why I think that fundamentally the model for C and compilers is broken. It should not be a gigantic mystery what kind of x64 code is going to get generated when you do something as simple as copy from a known value to memory, right? It should be like really straightforward. And the problem is we keep introducing all these layers, switches, and optimization passes and all that stuff. Just let's stop all that. If there's not straightforward ways to optimize code from the C code, let's modify the C spec so that I can tell you what I was trying to do, right? And that's just better, right? I don't want this to be happening. This is bad, right? It makes the person's job a lot harder when they can't reliably know that copying from one place to another, if it's 64 bytes, should just be 4 MOV UPSs. That should just be like obvious. And if something other than that's going to happen, you should have to be specifying all kinds of like encode pragmas or something to get it to happen. Doing the obvious thing is way more valuable than occasionally doing some heroic thing, you know? So this is not tractable. It's not great, right? Is it possible the extra jumps Clang generates are a specter mitigation? Why is it doing specter mitigation? Nobody asked it to do specter mitigation. In what universe would I care about specter mitigation in a game? Right? It's absurd. It's absurd. If you want specter mitigation, you should have to ask for it. Now, I don't know if that had anything to do with spectrum mitigation, but if, let's say that you're right and it did, it's absurd that it was doing that by default. I'm trying to test this code and it's doing spectrum mitigation? Well, that's something I should have asked for, right? All right. So if you want to share this Godbolt as well, here is a link to it. It'll probably save it, and then we'll close down for the day. Oh, someone says spectrum mitigation is on a hardware level. Spectrum mitigation at the hardware level is only in some processors, right? And they had to do like patches for it, but again, I don't think that was spectrum mitigation or anything anyway. But I'm just saying, let's suppose it was. I don't see how it would be, but let's just suppose it was. That's dumb anyway, right? It shouldn't just be throwing spectrum mitigation in the middle of something that I didn't ask for. So either way, it's dumb, right? So anyway. So here's the Godbolt link if you want to jump to it yourself and play around, which if you're trying to learn assembly language, I highly recommend you do. I guess all I can say is it surprised even me how bad this clan code was. I really don't like that. I guess I'll be more aware nowadays to double check anytime I'm compiling with Clang that it's not doing something really heinous to mem set loops, basically. So now I know. All right, let's close it down. Thank you, everyone, for joining me for the first episode back of Handmade Hero. It's been a while. Thanks for coming back and joining us. If you want to follow along this series at home, you can always pre-order the game at handmadehero.org. We're going to start working on that soon, maybe next week. But I want to start off with a chat, and I did want to address that Twitter thread because I appreciated Jesse taking the time to actually do some testing and some timing. So that's it for this week. I'm going to do limited, since I'm working on Star Code Galaxy right now, which is the upcoming code class. I'm actually working pretty hard to try and get it finalized. Since I'm working on this right now, there's going to be limited Handmade Heroes only once a weekend, just to save my voice so I can have a day off and not get too much laryngitis. So it's a limited schedule, but I will be here once a week just to say hi to y'all and to also make a little bit of progress on the game while we wait. And then after our Star Code Galaxy is out, we'll start resuming regularly scheduled programming. So thanks for joining. I'll see you back here next week. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.